Dear ladies and gentlemen, sorry, but please join the table.
No COVID-19 anymore, so it can be closed.
We can be close. Pandemic is over.
Yeah.
We all are vaccinated, so don't be afraid of your neighbors. Everything is fine. Very good. And dear ladies and gentlemen, it's a great honor for the Academy of Sciences of Lithuania. We have a Chancellor of China Medical University from Taiwan, very prominent guest. I'm afraid to pronounce the name. Sorry on my Chinese pronunciation. Mian Chi.
Okay. Now you sound like a Taiwanese. When you pronounce it, it's more like a Chinese. But they understand.
Okay, thank you very much. And the President of China Medical University, academician, Academy of Sciences Taiwan, Academy Sinica, and this excellent guest, which we are very proud of it, that we have him as a guest. He will give a lecture of Mget-guided effective therapy, which is, what I am medical doctors. And to Professor Chaplinskas, I can tell that in Lithuania it's a word, and to our prominent professor of oncology, I can tell that from time to time, or after some time, everyone is keen to go to hospital and to get a treatment. So it's very vitally important for all of us. So please, the floor is yours. Please give a lecture and we will enjoy it, I'm sure.
Okay, I just can add a few words from the medical community. It's a great pleasure and extraordinary opportunity to hear a lecture today, because my short introduction about Professor Ming-Chi Hong, right? So Professor Ming-Chi Hong is President of China Medical University and Chancellor of China Medical University, Asia University System in Taiwan. He is regarded as one of the best, if not the best, cancer researcher in Taiwan. He was selected as one of highly cited researchers in crossfield in 2021 among world's top 2 or 1% best scientists in the field of cancer research. And he was selected in 2021 highly cited research in Clarivate Analytics Web of Science. So his research includes translational research, signaling transduction, breast cancer, immune checkpoint therapy, and resistant mechanisms. He had many awards and honors. He has published more than 600 peer-reviewed research articles in journals such as Nature, Nature Medicine, Nature Cell Biology, Nature Cancer, and so on. And he also serves as editor, chief editor, or editorial member for many journals in the field. So, great honor, and please, Professor.
So it's my turn now? I'm waiting. Hey, this, please.
Oh, yeah, sure.
The first time I came to this country, so I had to make a friend. So one way to make a friend is by this. Okay. So after this second, we are all friends now. So next time when we meet each other, well, in Taiwan or in whatever international conference, please say hi. Say, hey, you're my friend. Okay. So I'm glad that I have this opportunity to come here. This is the first time I visit this country, and I'm coming here not just for sightseeing. Well, tomorrow morning maybe we'll do a little bit. But, can you hear me? Yeah. But I really come here to looking for, let me see, I using the, I can use the mouse, right? Okay. Yeah. I'm really looking for collaboration opportunity. You know, you probably know better than me. Now, your country and my country, Taiwan. You're like a brother now, right? Like a brother, you know. Or you want to say sister, it's fine. Brother, sister is the same, anyway. Okay, so I'm really coming here to looking for potential cooperation opportunity. So I assume that except for him, all the rest are biomedical field. Am I correct? You're a physician.
Yes,
yeah. You're a physician.
I am out of I will tell, nobody is perfect.
And when I talk, I know I do appreciate that you give me a lot of time because I'm a big mouth. You probably can tell already. So I like to talk. And so, but usually when I go to give a talk, they give me 30 minutes, 40 minutes, 1 hour. I never finish. I always, over time. So but here I know I have a lot of time. Okay. So I'm going to speak very slowly. By the way, I assume how many people are working on cancer field? Yeah, okay, 50%. Okay, I'm going to speak at kind of a reasonable pace. And then if I have anything not clear, please feel free to stop my talk so I'll answer. I promise you I will not answer in Chinese or Taiwanese. I will answer in English, okay, although I cannot answer in your language. Okay, so how many people do not know this lady? Raise your hand. Oh, you don't know, right? Okay. So, well, even the war that when Russia attacked the Ukraine, right? She came to donate money to try to help. I got to know her. At least know she's a pretty lady. Whatever you expect, right? However, we all know that she's a movie star. But in 2013, she made a very big decision. And you probably know that. Because she was diagnosed as a family, in her family, there's a gene called BRCA, breast cancer gene, by the way. And this represents breast cancer. Are you working on breast cancer? No. Yes. The reason I ask that is not because you're female. It's because of the color. Your color, pink color. That stands for breast cancer in U.S., in Taiwan too, okay? So because she's a family, she has a genetic disease. So based on statistic data, she knows by age of 40, her chance to develop breast cancer or ovarian cancer is more than 80%. And back to 2013, at that time, I am sorry, that disease, no cure. When I say no cure, meaning what? Meaning once you diagnose to have that kind of breast cancer or that kind of ovarian cancer, you're dying, period. I mean, she's a smart lady, right? So she decided, hey, forget it. So we remove her breast and later on remove her ovary. And now she's okay. Although she has a lawsuit with her ex-husband right now. I don't know how many people read those news. Well, anyway. And the reason why she did that is because of the BRCA gene, stands for breast cancer number 1 gene or breast cancer number 2. And for the BRCA gene, and this person, you may not know her now, but she's a close friend of mine, Mary Clara King. She is a scientist. She is the one who identified and involved cloning of the BRCA gene. Before her time, we don't even know why that disease caused a cancer patient death. But now the gene is cloned, and now it has become a routine diagnosis, and now even has a drug now. And so let me just briefly share with you scientifically why this gene is so important. We are all human beings, and all our cells has a very important DNA repair activity. The reason why all cells need a DNA repair activity because our cells exposed to all different kind of carcinogen, sunshine, smoking or whatever, and that causes mutation. And when a cell mutated in such a bad way, either cell die or cell don't die, become bad cell, and become a cancer, something like that, okay? So, it is important to have our cell, to protect our cell, to have a DNA repair activity. And in our human body, there are 2 major DNA repair activity, 2 major ones. And if you want to talk about detail, there are a lot of minor ones, okay? The first one is so-called, if you're exposed to carcinogen, the first thing happened in DNA, double strand, right? Watson and quicker. But you have a single point mutation. And that single point mutation, we have a one pathway called PARP. This is the enzyme, pyrylation. And go to this one, go to polymerase ligase, and then this single strand DNA mutation will be repaired. So you'll be normal, no problem. However, sometimes when this mutation stops for too long, it will become a double-strand DNA break. Once, you have a double-strand, Watson and Crick, right? Once you have a double-strand break, what happened? The two DNA is difficult to repair. So that there's another pathway called hormonal recombination DNA pathway. That's this pathway. And so we have two pathways. It doesn't matter if you don't know the detail. It's just one A pathway, the other one B pathway. And what happened to the BRCA family is that particular family, the germline gene, the BRCA, either one or two, can I have mouse compact? Oh yeah. When the gene is mutated, this gene has function in this hormonal recombinant DNA pathway. So when this gene mutation in that particular family, you know what happened? We all have a two copy of gene, right? So once you have mutation, you have one gene mutated, no function. You only have one left. Once this one mutated, then this cell is very easy to develop breast cancer and ovarian cancer. And there's a reason why that is the case. And therefore, this type of gene, after being discovered by Mary Clary King, and predicted that the family is very easy to develop breast cancer or ovarian cancer. And that's why that beautiful lady decided to remove her breast and ovary. Her surgery happened in 2013. And the first drug being approved by US FDA, actually developed from AstraZeneca, olaparib, for treating ovarian cancer, it's the end of 2014. And nowadays, there are many drugs being approved now. And this is one of the early clinical trial on ovarian cancer. All this is patient survival. And then all these patients are ovarian cancer patients with a BRCA mutation. And if you don't treat them, the survival curve is like this red line. And if you treat with this drug, the survival curve is this green line. And my friend, this is a curve, but this curve is not come from Drosophila, it's not come from sea urchin, it's not come from mouse. My friend, every spot is one woman's life. Period. Every spot in this curve is one woman's life. And from red line straight to green line. Is that impressive? So as a scientist, for lifetime committed to the anti-cancer, when we see this one, it's very pleased. But we always challenge ourselves. Why not 100%? And that's ovarian cancer. And later on, the breast cancer in 2018, January and October, two drugs all been approved for breast cancer. And their objective survival rate, you can see this curve that one is worse and the other one is better because of after treatment. Keep in mind, for those cancer patients, if they can expand their lifespan half year or 1 year, it's very significant. It's very significant, okay? Otherwise, they have a limited amount of time. But we as a scientist, and I'm certainly hoping you, some of you are clinicians, some of you are scientists, we have an agreement that it is our responsibility to make it 100%. Of course, 100%, you probably, maybe some of you are laughing at me right now. That's impossible. Of course, that's impossible. And that's why we work on it. And cancer is impossible when I was young. I'm 70 years old. 50 years ago, in Taiwan, nobody wanted to talk about cancer. You know why? Because you don't even know what causes cancer. And then if a family has a cancer, you don't even know what causes cancer. And then you have no cure. So first, I have cancer, I'm going to die. And second, what's wrong with me? Did I do anything wrong in my last life? That's why I become cancer patient. 50 years ago, that's the way it is. Now, we know that's not the case. It's just because you're unlucky that your normal gene be mutated, not repair, and so normal cell develop cancer cell. So gradually, every time when you develop a new drug, you make that impossible curve, the survival curve, switch to longer survival, and gradually, step by step, eventually reach 100%. My friend, oh, by the way, are you my friend now? We consider our friend now, okay? So start from now on, when you see each other, we are your friend. Cancer has two different types. One is so-called liquid cancer, it can leukemia, lymphoma, they are more homogeneous. The other one called solid tumor, the breast cancer, lung cancer, liver cancer, they are solid tumor. Liquid cancer is homogeneous, it's easier to be developed treatment. As a matter of fact, CML, one of the leukemia, now it's been considered cured because 90% of the diagnosed patient can live for more than 5 years, tumor-free for 90%. So that disease is being considered cured. However, solid tumor, I'm talking about breast cancer, I'm talking about prostate cancer, I'm talking about liver cancer, I'm talking about lung cancer, is not being cured yet. We still have a lot of effort that we need to do. And I'm hoping that today's lecture and then with your expertise that we could work together sometime in the future to reach that impossible dream. So let me share with you that why this 100%, all these breast cancer or lung cancer tumor in which you have the BRCA mutation, why not all of them respond? Some of them apparently respond. So we actually do a lot of study, try to figure out why they are the same type of breast cancer, the same type of ovarian cancer, and they have the same type of BRCA mutation, but why some work, but some don't. Now, make a long story short, in this Nature Medicine article a few years ago when I was in MD Anderson, we noticed in one type of breast cancer called triple negative breast cancer, which is a very difficult disease to cure. That type of breast cancer, there's a gene called those receptor tyrosine kinase called Cmet. This Cmet receptor tyrosine kinase is known to be overexpressed, activated in triple negative breast cancer about 30%. And that 30% of the breast cancer will not respond to PARP inhibitor, even their BRCA mutation. The reason is we in this, oh, by the way, you may be life science interested, maybe would be interested in something like this. This is the structure functional interaction. So what we found is PARP inhibitor is a small molecule, organic compound. And binding to PARP is an enzyme. After binding, so you block enzyme activity, so you inhibit this enzyme activity, and therefore that the cancer cell can be killed. But if cancer cell has this Cmet overexpression, what happens is the Cmet would phosphorylate PARP at the tyrosine 907. And after this phosphorylation, now this enzyme no longer be able to bind into PARP inhibitor. And if an enzyme cannot bind into the drug has no effect to kill the cancer cell. Okay, so that's why we call it resistant. And then luckily, Cmet also have an FDA-approved drug. So in the animal model, we show that combination can cure those resistant animals. Those are animals who have a breast cancer, BRCA mutation, and PARP inhibitor resistant, but when you do combination, it works. And currently now, based on this animal data, the clinical trial done by Dr. Tim Ye, who is my friend in MD Anderson, and he has not published yet, but he told me that the data looks pretty good. I.e., they identify specific marker by Cmet, which, we develop method, and then to identify the right patient to be treated the right drug. So with that in mind, that was a few years ago, not 6 years ago. And continually, we have been doing this kind of step. And now we identify multiple enzymes caused resistance by different mechanisms. And then the most recent one, just this is going to come out Nature Cancer probably next month, we identify another kinase called ALK. I don't know how many people here has dealt with the lung cancer, or anybody working on lung cancer? Yeah, okay, no, that's fine. If somebody doing lung cancer, ALK, this kinase, is known to cause about 5 to 6% of non-small cell lung cancer. And then the lung cancer, in the lung cancer, the gene was rearranged. And there's a drug. to deal with that. So what we found the following. This ALK enzyme in ovarian cancer and in breast cancer can go through this specific pathway to enhance DNA repair activity. And its enhanced DNA repair activity will cause a PARP inhibitor resistance because, you block the enzyme activity, but the DNA activity, repair activity was recovered. Therefore, in order to overcome this type of resistant cell, now we have to use ALK and ALK inhibitor and the PARP inhibitor. Both of them are FDA approved. Let me emphasize, we on purpose try to do this kind of novel combination using FDA approved drug because we can identify patient and I don't have to develop drug. We can cure patient right away. Because you know how long it takes to develop anti-cancer drug or small molecule? 10 years? 20 years? Right? I cannot wait. The patient are dying. We are trying to looking for existing drug to identify the right patient to be treated the right drug. Also, here, just show you the animal data here. This is the animal survival. Triple-negative breast cancer again. Without treatment, all the animal die, 40 days, highly malignant. If only one drug PARP inhibitor because of this resistant, it still die. And then you use another ALK inhibitor, it still die. But only when you use an ALK inhibitor, which FDA approved, and the PARP inhibitor, FDA approved. Together, my friend, this is red line. Hey, 100% survive. Animal, it's not human. Hey, come on, give me a break. Hey, 100% survive. Hey, am I your friend? If this is correct, if it's showing the human, that better be nice to me. I'll be very rich. I have a patent protection. And it's not probably not the most important thing. But the important thing is in animal, those animals die because of cancer, but with this combination, tumor size shrink and animals survive. So, can we apply to human? We have not done clinical trial yet, but I'm going to show you what we could do at this moment because we have a lot of this combination. This is a patient picture. This is a head and neck cancer, and here's a human head, and here, there's a big tumor here. This is a head and neck cancer with a BRCA mutation. When this patient, the end of last year, the physician already claimed they try anything. They try PARP inhibitor, it doesn't work, and the clinical condition is so poor, they expect he is going to die in 1 month. Impossible to live longer than 1 month. And we happen to have a cooperation with that physician, and then I told him that it's a PARP inhibitor resistant. Do you have a whole genome sequencing? Nowadays, a lot of patients, their DNA was doing the sequence to see what other gene was mutated. And happened to be one of the genes is kinase. And that kinase we already know causes resistance. And so I suggest, well, is it possible to try this kinase inhibitor, which happen to be FDA approved? If it's not FDA approved, we cannot do it. So the FDA approved drug, and this patient does not respond to PARP inhibitor, and this enzyme causes resistance is already activated in this patient. So use combination. Does he alive? No. But does he live longer? Yes. My friend, he lived for 6 more months. And my friend, this terminal disease, 6 months is a very long time. Because when they say die, they can quickly die. Okay, but eventually, by the end of May, I believe that he died not because of cancer, it's some other complication. But this tells us, although it's only one patient case, but looks like the study, the Mget study, we have a proof of concept. So we are talking to the pharmaceutical company, to them, because that's their drug. If they make money, we don't make money. So if we want to do a large-scale clinical trial, they put the money in, and then we can help them to make this drug to be able to FDA approve or apply to another indication, and then that can benefit the patient. So that's one example. And eventually, what we would like to do is so-called umbrella clinical trial. Umbrella clinical trial, by definition, is a multiple target therapy for a single disease. So let me use the BRCA mutation as a one single disease, like Angelina Jolie, that's a one single disease, breast cancer, BRCA mutation, or ovarian cancer, BRCA mutation. In the future, what we would like to see is when a patient comes to the clinic, and then you diagnose the BRCA mutation, you could take a small amount of tumor tissue, do a mini antibody array, like this one. And so we can spot a lot of antibody against different kind of phosphorylation of enzyme. Those are enzyme culture resistant. So we can, before patient being treated with a PARP inhibitor, we can identify, is it possible this patient will culture resistant? And what gene causes their resistance? Then under that situation, we will be able to directly use the combination therapy to treat this patient. That's the goal. So the goal is to be able to increase the patient's survival rate. So that's a solid tumor and using the marker which is from human tumor. But if a marker can come from, not from tumor, come from serum or come from urine, it will be much easier. Because if it come from tumor, you have to do surgery. But if it come from serum, you can just suck out the blood and then you can diagnose it. So I want to share with you that we actually we are the first one who discover a family of gene can be served as a serum marker. All of you probably, I assume all of you have studied general biochemistry before. If you study general biochemistry, remember the first protein amino sequence, bovine serum, bovine ribonucleus, because bovine ribonucleus is a huge amount. So the first protein sequence determined was bovine ribonucleus. And the first three-dimensional structure is bovine ribonucleus. That's a textbook in biochemistry. And everybody knows that ribonucleus is, by definition, it's an enzyme degraded RNA. But what we discovered, and I don't want to go to the detail, that in this Cancer Cell article 2018, this paper was fighting for almost 2 years because nobody believed it. We report in pancreatic cancer ribonucleus 5. It's a ligand for EGF receptor. Hey, EGF receptor is a well-known receptor. And the mutation causes a lot of human cancer. And there are multiple, 6 or 7 ligands already identified. So we say ribonucleus 5 is a ligand, nobody believe it. The reviewer don't believe it. And so the reviewer pretty much asked us to do everything that we can possibly do to show ligand receptor interaction. And we did it. So we forced them to accept it. But at that time, we already know human, there are 13 ribonucleotides. That's why this morning when you told me that anhydrase is 12, the number is similar. Human has 13 ribonucleotides. So at that time we hypothesized that is it possible all these 13 ribonucleotides, they are all, if not all, most of them, many of them are ligand for other receptor tyrosine kinase. At that time, 2018, we don't know, but now we know that's the case. We already know ribonucleus 7 is ROS1 is another receptor tyrosine kinase ligand. Ribonucleus 1, EPH4. These are from our group. Last month, there's another group from Tufts University show ribonucleus 4 is a ligand for another receptor tyrosine kinase called X. So looks like it's real now. And here, just want to quickly share with you that at the time when we discovered this ribonucleus 7 and ROS1, it's the reason we chose ROS1 is because ROS1 is called orphan receptor. All these receptors, when they have a ligand, then you have a ligand receptor interaction, but there are some receptor ligand cannot be discovered. So before they identify ligand, so we call it the orphan receptor. It's just like a guy who will not get married, call it a single, right? Or well, female we call single too. But after married, you don't call them single now. They're married couple, right? So ROS1 is the last orphan receptor at that time. So therefore we purify all 13, we clone all 13 human ribonucleus, purify all of them, and then show, is it possible any one of them turn out to be the ROS1 ligand? And you can see this number 7 is the only one binding to ROS1. And all these are the standard functional assay to show ligand receptor interaction. So now we have a receptor tyrosine kinase ROS1 has a wild type ligand now. And why this is important? For lung cancer is the number 1 killer in human cancer, okay? In terms of number of death. Lung cancer, ROS1 is known to be mutated. This mutation is by rearrangement, and about 5 to 6%. And pharmaceutical company already developed a drug. So the first drug resulting in the second generation drug, and then the third generation drug come out. And this drug will target this ROS1 mutation and inhibit. And here is a clinical trial of the lung cancer clinical trial result, 70% response. So the drug was a fast accelerated approval. Accelerated approval meaning by phase 2 they already approved to treat the lung cancer with this type of rearrangement. And okay, so that's in lung cancer. But remember, people did not know there's a lichen. So now we discovered riboneuclease 7 is a lichen for receptor tyrosine RS1. Then we show in this article that this lichen receptor interaction, their signal pathway is virtually identical to the rearranged gene. Because this rearranged gene, the mutated gene is considered activated. But this wild type gene, after lichen stimulation, their signal pathway is the same and contribute to liver cancer. Then we show that under that situation, then liver cancer can be treated by this type of drug under animal model. And the nice thing, that's what I want to emphasize, riboneuclease 7 is a lichen. You can detect it from serum. So the patient coming to the hospital, before they've been surgery to cut the tumor, if we take out the serum and detect the riboneuclease 7 level is too high, they may have a potential to develop liver cancer. So with that in mind, so then that was at the time when I did this experiment, pretty much done in the US, but then I went to Taiwan, and this 5 patient in Taiwan. So what we did at that time is the liver cancer patient come in, then we take their blood, measure riboneuclease 7 level to see whether lichen increase or not. Then after that we treat this drug and to see whether the extended lifespan can be proportional to the riboneuclease 7 level. Because when you have more lichen, you stimulate more receptor interaction. Okay, my friend. I always call you my friend. You have to consider I'm your friend, okay? I call you my friend 3 times already. And by the time when I finish the talk, I probably say my friend 20 times. So we are friends, okay? These 5 patients are liver cancer patients and has no option. Keep in mind, this type of trial, we cannot say, hey, I'm phase 1, I'm stage 1 cancer, I want to test this drug. No, that's illegal. If you are stage 1 or stage 2 patient, you should use the one FDA-approved drug, approved for this disease. But here we are talking about those terminal disease, so you probably know this better than anyone else. They don't have any option. All the so-called new drug, all of them fail, and they have no option. And then we take out a serum. We're not saying every patient will be treated, but if the serum level, riboneuclease 7 level is high, then we have a drug. Then we test it. See, here, y-axis is riboneuclease 7 level of those patients' serum. And x-axis is survival time. It's not linear, but 5 patients only is close to linear. Unfortunately, not all of them survive. So up to now, there are only 2 survive, but eventually they are likely to die. But their lifespan is extended. So, i.e., this direction is correct. So we are planning to expand this using serum marker to select patients to be tried with this trial to see whether we can really statistically significant to show that the patient life can be really prolonged. And again, the drug, we don't own the drug. Drug owned by a pharmaceutical company. They make money. But we own the marker. We can identify the right patient to be treated the right drug. Okay? So mainly it's to help, well, if it's a cancer patient, and if there's no drug, then the patient is supposed to die, they're supposed to die. What else you can do, right? But there's a drug, already FDA approved to treat other cancer type. But you have a marker to say, hey, this drug may help you to survive for 1 year, 2 years. Why not do it? Okay, that's the purpose. So that's one example. And sorry, how many people read Chinese? Test Chinese. Or maybe he read. Okay. This Chinese book is called 黄帝内经. At this moment, This was written 1,000 years ago, okay? And nobody knows who wrote the book, this book. We cannot find who wrote the book already. But this is the first Chinese medicine book. And this book saying that Chinese philosophy was saying, when you deal with the disease, there are two very important factors. One is, okay, if I say Chinese, you don't know, 气血 and 扶正. The 气血 is, one is, if you cure a disease, two factors are important. One is eliminating evil. Assuming the cancer, meaning kill the cancer cell, right? You kill cancer cell, then you kill the disease. But that's not enough. The other thing is to have to strengthen your body resistance. It's just like how many people have taken the COVID-19 vaccine? I took it 4 times already. So why we have to take the vaccine? To enhance our immune response. Right? Although the vaccine may not work as what we expect to see, but that's the strengthen your immunity. So 1,000 years ago, this Chinese medicine book already said that to cure a disease, including cancer, you have to do 2 things. One, cure cancer cell. The other one, enhance your immune response. Right? So you become Superman. So nobody can kill you. This is not only cancer. COVID-19 is the same too. Okay? Well, the theory is known for a long time. But human being, it's a little bit slower that not until when Jim Allison and Tasuku Hongzhou that discovered immuno checkpoint therapy, which some of you may be aware that Jim Allison developed anti-CTLA-4 and that Hongzhou developed anti-PD-1 antibody. And that in the cancer therapy field become a revolution because they are really, I'll explain why they only enhance your immune response. They don't kill cancer cell. They don't kill cancer cell. They help your T cell to kill cancer cell. Okay? And, well, everybody is interested in Nobel Prize. In 2018, they received it. In 2018, I still named it. I came back to Taiwan in 2019. So Jim, I was a VP basic research. Okay, so Jim is the faculty over there. So we're friends. And then I was just ready to leave, so we took the picture. And that year, when Nobel Prize was announced, not just recently, right? October, right? But no November time, when I go to work, it's very strange, in our parking lot, there are a lot of students, a lot of young kids, standing in one of the car, taking a picture. I just, what the heck is it? Why car is so attractive? Everybody want to take a picture with the car. So I went over there to see. Holy shit. Sorry, excuse my language, okay? This is Jim's car. This is Porsche, right? You know, a sport car, nice. But you know, the license plate is Texas CTLA-4. And CTLA-4, anti-CTLA-4 is the drug he developed. So that's his license plate. And after he got the Nobel Prize, every student go to take a picture. And when I saw that, I said, hey, I also took a picture too, but I didn't take a picture by myself. I just took that picture. So that's his car's picture. Okay, let's share with you. Why these 2 persons get Nobel Prize? Because I told you that Chinese medicine book is saying, you have to kill cancer cell, right? But kill cancer is not sufficient. You have to strengthen your immune response, right? Let me just oversimplify to say what is this immuno checkpoint therapy. All right, bear with me. This is tumor cell. And tumor cell come from normal cell, mutation, right? And you cannot repair that. So once tumor cell from normal cell become a tumor cell, it develops some sort of so-called tumor antigen. And this tumor antigen could be some sort of gene overexpression or mutation or something. And, no, I'm sorry, this is tumor cell. Tumor cell, this is tumor antigen. Okay, so this tumor cell develops tumor antigen. And however, human body, we have our own policeman. Our policeman is a T cell. Okay, T cell will come to say, this is T cell, come to say, hey, go to T cell receptor, tell, oh, this is antigen, this is a tumor antigen, this is a very unusual, this is not normal, this guy is a bad guy. So T cell, through T cell receptor recognize the tumor antigen of tumor cell. So this signal will allow T cell to kill the tumor cell. Just like a policeman go to the bad guy to grab the bad guy, put in the jail, right? But wait a minute. Why they call bad guy? Bad guy is not stupid. If bad guy is stupid, they cannot be bad guy. They're smart. They're smart. And you know how smart? I don't know whether that happened in this country. In Taiwan, it used to be that way, but now it's better. So if you were caught by policemen and you were not to jump out of the chopper, can you at the night time go to the police house and give, under table, say how much money? 10,000 or 100,000 or maybe $1 million, right? A channel to, pass money, right? Then after that, second day, you're free, right? Hey, tumor cell do the same thing. I'm not kidding. Tumor cell, this tumor antigen was recognized by T cell. So in order for tumor cell to survive, tumor cell produces this protein called PD-L1. And PD-L1 to do what? Because tumor cell produces PD-L1. But T cell, well, I cannot say, this is tumor cell, this is T cell. Tumor cells produce PD-L1, and the PD-1 inherited the PD-1 cell surface protein of T cell. So once this interaction happens, you know what happened? These tumor cells tell the T cell, this bad guy tell the policeman, say, hey, we all come from the same country, God, don't grab me. On the table, how much money you need. So this signal, the bottom signal, PD-1, tell T cell, don't kill tumor cell. That's why tumor cell survive. That's why bad guys survive. The police don't grab the bad guy. But you know what is why those two people they get the Nobel Prize? Because they discovered this theory and developed antibody. And this antibody can be either against PD-L1 or PD-1 or PD-L1. So once antibody binding, then these two cannot bind. So this under table channel disappear. No more under table. Everybody have followed the rule. So you're a bad guy, I put in your jail. Okay? That's immune checkpoint therapy. Hey, because of this survey, they got a Nobel Prize. Why not you get Nobel Prize? It's very easy. Well, come on. Why you bribe the police? Everybody knows that. But remember, 2018, the two Nobel Prize winners for physiology, it's because of this theory. And so they don't really develop a drug to kill cancer cell. No. They only tell the T cell to really kill tumor cell. Enhance your T cell activity. Okay? Well, anyway, they get Nobel Prize. Don't complain about it. Okay? And at least I know him, right? Okay? So now, this is their clinical trial. This is melanoma. This type of cancer in the terminal disease, before this drug available, 80% to 90% die within 1 year, meaning 12 months. 12 months a year. But after these two drugs available, this clinical trial, anti-CTLA-4, medicine, 5-year survival rate, 8%, anti-PD-1, 29%, combined together, 36%. Hey, my friend. Hey, again, I say my friend. Count how many times I've said my friend. Okay, we are friends. This is a 60 month. 60 months is what, how many years? 5-year survival. They are tumor-free. Pretty much they are tumor-free now. So this disease, this patient used to be 80 to 90% die in 1 year. Now with this drug available, these two drugs available, 36% of them are tumor-free for 5 years. Do they deserve a Nobel Prize? I think they deserve it. Okay, even I don't get money. They will deserve it. So that's why I get Nobel Prize. But now, again, why not 100%? Why not 100%? And when I work in MD Anderson, when we see a drug like this, we're all very happy. But we always ask, why not 100%? And then you say, 100%, that's impossible. Or you say, they should do it. Who are they? Who are they? We are they. Well, who got to do it? What, they? Who are they? The taxi driver? Or worker? No, we, scientists and physicians, got to do it. And of course, it's impossible, but every possible thing is come from impossible anyway. So we challenge on this one. And here, let me just quickly share with you that our approach. Let me skip this slide. We also develop antibody against PD-1. This is antibody structure. But in order to make sure we can efficiently kill this tumor cell, you know what we did? There's a trick called the antibody-drug conjugate. So this antibody can recognize PD-1. But that's not sufficient because solid tumor is heterogeneous. You needed to induce the bystander effect. So in order to do that, we then link this antibody with a small molecule. These are very toxic chemotherapeutic drug. So with this antibody-drug conjugate, then when you test in the animal model, look at the animal survival. Triple-negative breast cancer, again, without treatment, they die. Antibody alone, 25% survive. This is a percentage human data. But this antibody-drug conjugate, my friend, this is the line. One drug only. The green line is the one FDA approved. The red line is the one we developed. Of course, it's not FDA approved yet. But if that can be tested in human, if you were a cancer patient, which one are you going to choose? The red line or the blue line? This is 70%, this is 25% survival. Hey, be smart. Okay, so now this one was licensed to a company in Taiwan. Then we try to, pharmaceutical scale and then try to take clinical trial. And here, this antibody drug, I don't want to say that the antibody drug conjugate is now a standard way to develop drug now. Okay? And it's induced bystander effect. Hey, how many people know? You probably don't know. Don't pretend you know if I ask you. Do you know what is bystander effect? Okay, I mentioned liquid cancer and solid tumor are different, right? Liquid cancer is homogeneous. You develop one way, one drug, you kill them. But solid tumor is heterogeneous. Let's assuming, okay, we close the door. Everybody inside this room, we are a tumor. Just hypothetical, okay? Don't worry, you are not tumor, but I'm not hypothetical. And each one of us are a tumor cell. How about that? Now, can I ask you? 3 of you, 2 without glasses. You wear glasses. You, the breast cancer lady, without glasses. Then you with glasses. And he without glasses. Is it heterogeneous? It's heterogeneous. Because solid tumor is like that. So if I assume a solid tumor, there are millions of tumor cells there. All these tumor cells, not everyone is PD-L1 positive. Some are PD-L1 positive, some are PD-L1 negative. So they are heterogeneous. Now, you said you develop antibody against the PD-L1 as a drug, right? So I assume wear glasses. Oh, okay, wear glasses, okay? This is PD-L1 positive. So you are PD-L1 positive. You are PD-L1 positive. But you don't wear glasses, you are PD-L1 negative. So if I develop a drug against the PD-L1, I selected only target PD-L1 positive tumor cell. Only those wear glasses. Don't smile, you're going to die. Right, you're going to die. You wear glasses, you are PD-L1 positive. Because the drug will only kill you. It does not kill her, it does not kill him. Then the lady behind, next to, you die too, I'm sorry. Because you are PD-L1 positive. You know what does bystander effect mean? Meaning if I develop a drug, I'm target PD-L1 positive. Wear glasses, you die. But if it's a solid tumor together, even if you don't wear glasses, I'm sorry, you die too. That's so-called bystander effect. Okay, let me show you the result. Okay, look at this one slide. This yellow bar is a breast cancer cell. Wear glasses, meaning PD-L1 positive. So if I use this antibody drug conjugate, you treat it and the tumor cell killed. 100%, and most of them under this condition, 5% survive. But I know here you have a special technology to gene editing, right? I mean, you guys in the life sciences, you have some famous professor work on gene editing. So if I take this yellow tumor cell, PD-L1 positive, using gene editing, just knock it down. So now this black cell, black color, is the same cell as this yellow one, except PD-L1 knockdown. So I originally like this. I am wear glasses. I'm PD-1 positive. And knock it down, I'm negative. Okay? So now if I use this drug kill, if I wear it, I'm like this yellow one, I'm dying. But if I take it out, then I like this black color, I don't die. Okay, that's fine. Which that's supposed to, it should be the way, right? So this drug only kill PD-1 positive tumor cell. If PD-1 negative, no touch. Only wear glasses been killed. However, if you sit next to each other, I'm sorry, you just sit next to each other, very close. The red color, 1 to 1 mixed together, they all die. That's a bystander effect. Here's the in vitro, here's the in vivo. Anybody have this question? And we know the mechanism. There's the picture here, but I don't want to tell the mechanism. The bystander effect is a way that, you know. So when we develop anti-cancer drug, we really want to develop a drug. It's a target therapy, but at the same time, has a bystander effect. So solid tumor is heterogeneous, so you can kill. You target well, those who wear glasses, they're supposed to die. But because the tumors here are very close to each other, you don't wear glasses, you die too. The bystander effect. And the antibody drug conjugate has this ability. Okay? So that's one thing we are developing, try to see whether we can use this approach to cure cancer patients. The next thing I want to share with you is beta marker. Remember we talked about COVID-19? Everybody know, well, nobody wear glasses, nobody wear a mask now, but COVID-19 when it come out, there are a lot of so-called false negative or false positive. Am I correct? False negative, meaning I'm negative, but why I detected the positive, or false positive, false negative. Anyway, cancer is the same. PD-L1 has a lot of false negative. This is the clinical trial result. These 4 drugs are well-known FDA-approved anti-PD-1 or anti-PD-L1. And if we look at this black here, red line here, objective response rate, PD-L1 negative patient. Here is a positive patient. PD-L1 positive patient, and my friend, all these 4 drugs all have 31% response, 47% response, 83% response, 26% response. So that looks good, so FDA approve it. These are FDA approved drugs, PD-1 positive. However, in the clinical trial, everybody knows, some of them, this one, PD-1 negative. How come they still respond? Oh, if you are a patient, you say, well, if I treat the drug, as long as I respond in a tumor gone, I'm happy. Why care about PD-1 positive or negative, right? But medically or scientifically, it doesn't make sense. So this has been puzzled for a long time for the field. But now I can tell you, we actually discovered, and I say we, meaning we are the first one to discover, say, why this PD-1 negative respond? Because it's false negative. You know why it's false negative? Oh, okay, look at this one. A549 is a tumor cell line. S358 is an old tumor cell. This is a well-known tumor cell line. I put this one here because if you don't believe, you can get this cell line to do experiment in your lab. Very easy. Then you use the antibody, anti-PD-L1 to stand. This A549, when your PD-1 standing negative, right? Did you see any positive? Negative here. But this one is positive. So this one is PD-L1 positive, but this one is PD-1 negative. But this PD-1 negative is fake. You know why? Because PD-1 is heavily glycosylated. You know, you add a lot of sugar on it. PD-1 molecular weight is 32 kD, but full length, including glycosylation, is 52 kD. The large portion are glycosylation. And glycosylation are all in cell surface protein. So all the antibody using for diagnosis are all against the polypeptide, not against the sugar part. So for example, in this case, this cancer cell, negative, right? But if I use this enzyme, PNGSF, this commercial value enzyme, very cheap. Everybody, student can do that experiment too. When you treat the enzyme on this cell, the glycosylation is removed. Once glycosylation is removed, my friend, oh, my friend again, I just like to use it, my friend, so you are my friend. Then this one. The same cell, the same antibody, the only difference is you remove glycosylation. Isn't it positive or negative? This is negative, this is positive. So this negative is false negative. And we are very proud that we discovered this one with population cancer cell. And then here is a tissue microarray. You know the tissue microarray? The one I just showed you is a cell line. But then that one cell line, tissue microarray, meaning, okay, it's commercially available. You buy a tissue microarray, and on top of that, a lot of tumor tissue was a spot there. Then you use anti-PD-1 antibody to stain it. Then you say, okay, fine. What is the expression? That's the expression. This is white color. It's a very low level. And different kind of cancer type, you have, these are negative and some are positive, and these are some positive, some negative, okay? But if I use the same tissue microarray and go to that procedure, remove glycosylation by biochemical method, very easy. You can do in the lab because we figure out the condition already. Then after that, the same filter, you stain with the anti-PD-L1 antibody, red color. We estimate from cancer type to cancer type, 40 to 50% are false negative. That's why a lot of patients who are PD-L1 negative, they still respond because they are false negative. So under that situation, so we actually now develop method. So this is the patient who using the original without the glycosylation method, just a standard method, and looking for the progression-free survival and the PD-1 expression level. See, there's no correlation. This is PD-1 expression, and this is progression-free survival. There's no correlation. It doesn't matter, use this H-score or use the TPS, they are also the same. But once the same filter, you remove glycosylation, use the simple biochemical method, then you correlate with the progression-free survival, the red line. The p-value is much more significant. So with that, this is a very lucky patient. All these patients are Taiwan's patients that are in our hospital. I like to say this particular one. This is a lung cancer patient. Before treatment, it's a CT scanning, huge tumor here. After anti-PD-1 therapy, tumor gone. He's still alive. He's still alive. But he was lucky because at the time when he was treated with this drug, diagnosis kit not come out yet. So there's no diagnosis. And there's no diagnosis kit, but then the drug is available, and then health insurance company doesn't want to pay for it, but he has money, he pay by himself. So tumor shrink and he's alive. But retrospectively now, when we come back to those tumor tissue, we take the tissue out and using the current FDA-approved diagnostic kit to stain it. And my friend, this is negative. After this staining, when we remove glycosylation, using the method we developed, hey, it's positive. So this tells us this patient was lucky because he was treated with this drug before the diagnostic kit available. If diagnostic kit at that time available, the physician is going to tell him, don't do it because you're not going to work. It's negative. It's negative, but it works. Okay, so therefore, for scientists to develop diagnostic kit, one had to be make sure accurate. Otherwise, you could have this false negative, it would make it the patients who are supposed to be respond to the drug and cannot be treated. And with this another 9 patient. I don't know how many people know that. There's a big company called Mget, right, in San Francisco. They developed an anti-PD-1 therapy called, it was 2019. This drug was approved because of the clinical trial. You know what happened? 2019, the drug was approved. Acceleration approved because they say it worked very well. But 2 years later, 2021, the end of August, the company very painfully withdrew the drug. The drug is still working for lung cancer, for melanoma, for other cancer types, but for breast cancer, they withdraw. Because in the 2021, another clinical trial came out, it doesn't work. And you know why it doesn't work? It's not because the drug doesn't work. Because when the company developed this anti-PD-1 drug, They at the same time come with the diagnosed kit, say, hey, you have to use my antibody to detect your tumor, it's PD-L1 positive, and then therefore you can be treated. But the method is not accurate, it's wrong. So this 9 patient in Taiwan was a very lucky patient. They were breast cancer patient. They have no other option, and they are, I'm sorry, they're dying. They don't know what to do. And they talk to the physician, and the physician say, but there's a drug, Atizo. So, but let's do the diagnosis. All these 9 patients are PD-L1 negative, based on that the company's diagnostic kit. So you cannot use the drug. The insurance company is not going to pay for it. But they're going to die. And if I'm going to die, if I don't have money, I don't have money. If I'm going to die and I have money, and you tell me there's a drug and don't guarantee work, do you want to try? Well, of course I try. If I die, I get nothing anyway. And I still have money, so I try. So these 9 patients try. And look at the result. Out of 9, 7 of them, out of 9, 7 of them respond. Either complete response, partial response, stable disease. They life expand longer. Not all of them survive. Some survive, some don't. But 2 of them do not respond. Now, based on that FDA-approved diagnostic kit, all of them are not eligible. But now using the method we developed, these 2 patients, number 8, number 9, only look at the red color. Red color is our major method. The label is very low, right? Number 8, number 9. So they are progression disease. Progression disease means what? It doesn't work. So our prediction is correct because don't have PD-L1, it doesn't work. But number 1 to number 7, these 7 patients, all red color. Out of these 7, 6 of them are very high. And 2 of them complete respond. 2 of them partial respond. 3 of them stable disease. Some of them are still alive. So only 9 patients. So now in Taiwan, we link the entire Taiwan breast cancer community. By the way, Taiwan is a beautiful island, and if you have not visited yet, you should visit. And not only beautiful island, beautiful people too. The people who are physicians who cooperate to each other. We are from the north part of Taiwan to the south part of Taiwan. We are in the middle, okay? We have 6 or 7 hospitals joined together. We're going to prove, using different hospitals, patients who treated, and to show this method works. If that's the case, then this diagnostic kit should be used to select the right patient to prescribe the right drug. And who win? First, patient win, right? This patient is supposed to respond, then why you don't treat the drug? Second, who win? Of course, scientists and physicians win too because you can help patient to survive. The third person, third party who win, actually nothing to do with me. Genentech company, they own the drug. They have this drug been approved for other disease, but for breast cancer, they 2019 approved and 2021 withdraw. When I say that, you probably didn't realize how much money is that. Every anti-cancer drug in the United States, patent drug, every one of them, they sell, if it's not billion US dollar, at least 100 million US dollar. And so they already make money for 2 years. But the second year, because the trial doesn't work, so they withdraw. So it's very painful for them. But if this diagnostic kit work, this may be the first time in the history a drug been FDA approved, and then they told clinical trial fail and withdraw, and then they don't develop a better method and approve again. In history, that has not happened yet. I'm hoping that will be the case. By the way, how much time do I have? From 3:30 to what? Also, I still have some time. Okay. Because today I come here to looking for anybody might be interested in collaborate. So those are the specific examples I share with you. In addition to that, I have quite a few very, 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 very novel idea, and that can be tested in human. And maybe, so this Nature article 2 years ago, and this Nature Cell Biology article is just last year, that we all identify a new therapeutic target, and then we already screen, high throughput screen into small molecule. And so here, let me see. When my mouse, mouse come here. This is our screening. And this drug doesn't work, but this several drug, it seems to suppress. So here I just share with you that we have many of these type of projects which identify specific therapeutic target, then develop. We have a high throughput screening for small molecule to see which compound inhibit this enzyme. And then after that, then we will come back to very similar to a life science center. You approach it, the structural functional interaction, by crystallization, X-ray, and so on and so on. Okay, but bottom line is we identify therapeutic target, try to develop the small molecule that can inhibit this enzyme, and that can be tested in human. So, but today I probably don't have to talk about every specific project, but just to let you know, we have a lot of idea. The only thing we are missing is more people to work on it. We are not lacking of the project. We're just lacking of more people to work on it. Okay, now that's cancer. COVID-19. COVID-19, nobody wear mask. Actually, I did bring my mask, but I don't wear it because I wear it, I become mutant. You know what the definition between wild type and mutant? Majority is wild type. Minority is mutant. So if I wear this one, then I'm among this group, I'm mutant. I don't want to be mutant, so I take it off. Okay. And this is the number. Now we have this last month data. 6 million diagnosed at the moment. Not 6 million. 600 million diagnosed positive. 6 million people die for COVID-19. But COVID-19 after Omicron came out is not as bad now because it's just like a catching cold. Okay, it's not as bad. So 3 years ago when the COVID-19 started, as a university, we have a university social responsibility, right? So at that time COVID-19 came out, nobody knows what is COVID-19. Nobody knows how to deal with SARS-CoV-2. I don't know either. But we quickly form a team. And here is a mechanism that you may remember that this COVID-19, this is, my mouse, okay, mouse here. The COVID-19 virus, and here is the cell. And then you have spike protein interact with the SE2 receptor, then cleaved by transmembrane serine protease, and then eventually the virus go in there and release the genome RNA, produce all kinds of enzymes, including major protease, and so on. So at that time, we isolate all these protein and looking for, can we identify any natural product? At that time, we on purpose interested in natural product because Taiwan is agricultural. Taiwan industry is okay, but we have a lot of agricultural product. So I'm interested into the agricultural product to see whether any agricultural compound that might actually inhibit SARS-CoV-2. And make a long story short, one of the first one identified is tannic acid. We interested in tannic acid because tannic acid not only inhibit transmembrane serine protease, but also inhibited major protease. So one stone, two birds, because the two enzymes. Then one stone, two birds. So we thought, well, it's good. And plus, the nice thing is the tannic acid. And this just show you the one stone, two bird function. And you know what is tannic acid? And how many people drink red wine? Or how many people don't drink red wine? Raise your hand. I don't drink red wine. I don't drink wine, sorry. I'm a good boy, so I don't drink. So, anybody don't drink the red wine? You don't drink the red wine? Sorry for you. Tannic acid comes from grape. It's enriched in red wine. And so when this paper published, I did not on purpose to do anything. I was just kind of publish it, one stone, two birds. And later on, there was a TV from Taiwan, then go to Hong Kong, then once go to Hong Kong, go to all the world. So I received phone call from New York, from San Francisco, from France, from Canada. And then after that I said, don't call me again, because I don't have an answer for you. And all those phone calls is not patient. That was 2 years ago. When it come out, this was 2 years ago. 2 years Lunar New Year. So this is my small team. And then the TV come and then they talk about red wine. And you know what? All those reporters call me to talk about, none of them talk about COVID-19. They are all wine reporter. They are all wine reporter because, hey, tannic acid is rich as wine. Then there's a Taiwanese guy, Dr. Hong, say it's anti-COVID-19. So they try to sell that, say, so they can sell more red wine, or maybe red wine price is going up, something like that. So they call me. But they try to take out from me, say, hey, I can help them to sell. But I'm a scientist. I have to be honest, okay? So they actually interview me. And this guy is from San Francisco, Blake Gray. I heard that actually he is a very famous wine writer. And you can Google it, Blake Gray. You can Google it now. He's very famous. So I actually talked to him, and he wrote an article. So he tried to take out for me and say, hey, very nice you have all those making, but how many cups I need to drink one day that I will anti-SARS-CoV-2? And I didn't have that data, so we calculated that. So we didn't do human trial. So I told him, in principle, if assuming, practically that's another case, we can absorb 100% of everything we drink. Everybody's different anyway. Assuming I can only calculate that way. Assuming if I absorb 100% of all the alcohol I drink, and based on the alcohol content, tannic acid, you need to drink 3 liters each day to have the enough concentration into your blood. So apparently my answer is not what you want. Right? But I'm a scientist. I cannot just keep him say, oh, you can sell the red wine. But anyway, he wrote an article. And then at the end, he said, the last thing he said, that is me, okay, in our conversation was, stay safe and drink wine. But I didn't tell you should drink wine. However, having said that, we, as I mentioned, we are interested in the natural product. Tannic acid is not the only natural product. So tannic acid is a family. I don't know how many people know tannic acid is a family. So we actually continue our research, aside from the news reporter. Tannic acid, all these are tannin family. They are collagen and tannic acid and the OPC, all these are all tannic acid. So therefore, we actually study, and all of them are enriched in red wine, and grape too, especially grape seed. Okay, so we then do one by one, and then just let you know that you see the color different, right? Collagen is blue color, and it's a purple color, and tannic acid and the OPC is a green color. The reason I green color different is because when we test the different function, there are two groups of them. So this guy, all these three are tannic acid derivative. This guy actually block SE2 spike protein and the mPROT function much better than the other two. And then, however, these two, but not this one, actually can broadly inhibit different variant. Remember, we have a wild type from Wuhan, then we have an alpha strain, beta strain, delta strain, and until we have an Omicron strain, right? So you can see this purple color, wild type, they're okay. Alpha, okay. Now when you go to beta, the purple color is not as strong now. You know why? Because this purple color is this guy. And this guy inhibits SE2 and the spike protein. And what causes those variants? What is the beta strain come from? Delta variant come from? Omicron come from mutation in spike protein. right? It's come from mutation of spike protein. And so because your spike protein mutates so much, so this drug inhibit the wild type but not necessarily inhibit the strength, those variant. But anyway, we have done all this kind of stuff. Then I think in drink a red wine or eat a grape probably help, but I don't have human data to show how much you really have to drink. I don't, at least 3 liters. I don't know how many people drink 3 liters of wine. I don't drink anyway. So anybody drink a 3 liters of red wine every day? Probably not. Anyway.
What makes you red wine?
Oh, okay. So after that, I have received a lot of wine company to give me box by box, ask me to test it. So they want to say their content. Actually, for this derivative, the content is already known. All the red wine, each red wine, they all already know, and they are around that range. And at that time, I try not to run into trouble because when those news reporters call me, I know what they want. What they want is if I said 1 cup, COVID-19 free, then I'm in trouble, but he will be very happy. Right? I'll be in trouble, but he will be very happy. So I don't want to say something I cannot say. I'm a scientist. But anyway, so your question, yeah, those things already know. So let me quickly share with you that this is 16-acre, our new campus. We have an old campus, but out of our new campus, we almost double size our university. So, wow, actually, yeah, about double. Not as double much. So this 3 building is currently already completed, and my office is here. And then now this new biopark, and it should be ready next year. And then in this area, we will have another 6 this type of building as a biopark. And maybe I don't have to talk about all this. This already. This one, this is not existed yet. This was designed by Frank Gehry. I don't know, everybody know Frank Gehry? Frank Gehry is a very famous builder, designer. He's a world famous, he's 90 years old now. So this is going to be right next to my office. This is our Medical Innovation Museum. And it was designed such a way that hopefully once the building is ready, this will become a Taiwan mark. The surface are all in the metal. So the idea is at a different, when the weather is different, they have a different picture. So you have I don't know how to say that, in the morning you see this kind of picture, in the evening you can have a picture. So idea is to make a nice picture inside the campus. So for those of you who has been in Taiwan, please come more often. For those of you who are my friend, you are my friend anyway. If you have not been in Taiwan yet, please come. And when you come, you let him know. then we welcome you, okay? And by the way, we are very nice to students. This building is a dormitory. This building, in the nighttime, is this one. It actually received the French Novel Design Award. And in Taiwan, our university is the only one whose student dormitory received an international design award. And this is my office. Doesn't look any fancy, but this is our laboratory. There's a big eye here. And when this building is ready in our city, all the news reporters will report it, hey, this university has a big eye there. And okay, so that's Tim. We have a very strong cancer team. And I'm looking forward that your Academy of Science and China Medical University, we could work together. Because to end cancer, the COVID-19 is already end. And you know this guy? That's your friend. I got this one from this year. This is a surprise gift from our alumni party. And one of the alumni guy who is like to pen. So he, without letting me, I didn't know it. So he turned this one in our alumni party. He gave me the surprise, and then he was hanging there and cover it. And then at the time when he gave to me, he was, oh shit, that was me. So I'm now hanging that in my office right now. Okay, I think oh, by the way, do you know this sign? Make cancer history, this red line? This is the MD logo. And I still wear that. I wear this for 1996. More than 20 years, I wear this. And my brain is thinking to end cancer. So that's why we're always thinking about 100%. Because in MD Anderson, we have a 20,000 employee. Cancer only, nothing else. 20,000. We only deal with cancer. And so everything we do over there is thinking about 100%. And in the elevator, if you have a chance to visit MD Anderson in the elevator, don't worry about it. In the elevator, you will hear people talk about, oh, her breast and his liver and his lung. We will talk about cancer. One time I was in the elevator and it was someone else talking. And everybody talking about, oh, his lung and his liver. What? Then of course I work in MD Anderson, but then when I listen to someone is talking about, oh, we all the same, we all do that way. But in MD Anderson, that's your language. You don't say cancer because that cancer is, we only talk about organ disease. So it sounds like a horrible. Sounds like a horrible, okay? Anyway, so, and I've been there for 3 decades now. I went back to Taiwan for almost 4 years now. I'm still thinking how to make a cancer history. And I'm certainly looking forward that we have an opportunity to work together to make cancer history, okay? And, oh, the other thing, if you're interested, I actually run an online academician forum series. So every couple of months, I invite one big shot and online. So it's online anyway. So if just in case, just let me know if you're interested. Let me know. So we will share this online seminar with you. This was 2 weeks ago, and September 24, Mary Clark King, the person who discovered the clone, the BRCA gene, and Judy Garber is a Harvard Medical School physician. She actually running the clinical trial for a PARP inhibitor. And then we have a series of people, including my mentor, Robert Weinberg over in MIT, that on the line, every couple of months we have this online academician forum. Then in case people here are interested, and including faculty and students, and we'll be happy to just share with you that you can, because our time zone is not much different. Time zone is a 5-hour difference only, right? So, oh, wait a minute, 5 hours. If it's a 9 a.m. in Taiwan, it would be midnight here. 4 a.m. That's probably not practical. But if you have enough people, I'll make it into afternoon. If I make it into afternoon, then you could do in the morning. Depending on the speaker. If the speaker in the US, then there will be midnight there. Anyway, so just kind of let you know, I'm looking forward to, okay, I already talk a lot. We are my friends, so I better shut up and drink water and then let you talk.
Thank you very much for very inspiring, enthusiastic and promising talk. And I think many things that were impossible some time ago now are absolutely possible and are our daily or clinical routine. So let's hope that's the same true about the cancer treatment and cancer research.
By the way, are you you're a surgeon, right? Or you are?
No, I'm a neurologist.
A neurologist, yeah. Neurologist, yeah. Yeah, look, all those Nobel laureates, they all make something impossible possible. That's why they get the Nobel laureate. Because it's impossible, so make it impossible. Okay?
Thank you once again, and maybe some questions from the auditorium. Please don't shy and ask us what.
I know we are in different field, so any kind of question is okay. As long as you speak English, I'll answer in English. Don't ask your native language, which I have no idea what you're talking about. Sure.
Yeah. First of all, thank you so much. Thank you
Wait a minute. Oh, you touch my heart. In UT, I'm a foreigner in America, right? My English is not good, strongest. However, I'm the only one who was elected by graduate student, the best teacher of all time. Hey.
In this case, my question, what is written on your car license plate? Like best teacher or something from science, or what would be in the next your car plate?
You mean the car?
Yeah.
My car plate? Laboratory clone. When I was a postdoc fellow working with Bob Weinberg's lab, I actually cloned the rat version of HER2, called New. Actually, neuroblastoma. So I don't have that yet. But in the future, if I have that, I'll let you know. I'll take a picture and share with you.
Now serious question
About COVID vaccines. At least I don't found in mRNA vaccine in nanoparticle message is transferred to human cells. To which kind of cells? I mean muscles, stone.
So let me repeat the question. Are you saying that you're talking about nanoparticle, right?
Yeah.
How nanoparticle attack tumor cell, right?
Yeah, to each cell.
A specific tumor cell, right?
Specific cell.
Yeah, okay. Yeah, apparently nanoparticle has a lot of different way to attack tumor cell. Ideally, let's say there are a lot of tumor cells have the overexpression receptor. HER2 is one of them. EGFR receptor is another one. Cmet is another one. And that make a tumor cell, all those genes are normal genes, but the normal cell express low level, but tumor cell express 100 times higher. So therefore, it provides a therapeutic window. So if a nanoparticle, which can carry whatever drug you want to carry, mRNA therapy, chemotherapy or whatever drug, in the nanoparticle, if we could have an antibody to cell surface receptor of overexpression in human cancer, then the nanoparticle specific target is able to specifically target tumor cell. This may not be the only one way, but that's one way to do it. Yeah.
Okay. But what about vaccines?
What?
About vaccine, COVID vaccine. COVID-19 vaccine. To what kind of cells go? To muscles, digestive, I don't know.
Bone cells and so on. Which cells are producing
Okay.
this mechanism?
Talk about COVID-19. I think there are a lot of things we still don't know about COVID-19. In reality, 100 years ago, when Spain had that influenza virus came out, after 100 years, we still every year doing vaccine. And there are people still study the influenza structure and how to develop something. So COVID-19 just came out 2-3 years. We thought we know a lot of COVID-19. Actually, we don't. For example, we all talk about COVID-19 spike protein, interactive SE2 protein. That become like a common sense now. So even elementary school kid knows that, spike protein binding to SE2 protein. The SE2 protein as a receptor is very enriched in the lung-related cell. However, now people start to discover there are at least 3 reports that spike protein, in addition to SE2, could interact with the other receptor. And therefore, when you interact with the other receptor, it will cause different kind of symptoms. For example, remember, not Omicron, but earlier version of the SARS-CoV-2. Remember some of the patients when in fact they lost taste and lost smelling, right? I don't have a complete story yet, but there's one receptor which we discover in a cell is related to smelling. That receptor interacted with the spike protein. So whether that spike protein, by targeting that kind of cell and lost smell, that's a possibility. So I believe there will be more and more study coming out. And now since COVID-19, we got to live with it. You're not going to, the symptom is not as severe now. So, but who knows? We still need to continue to understand this disease, and then hopefully Omicron don't come out with another strain which give you a heavy symptom. So I know I did not answer your question, but the question is big because I'm sure 20 years from now, when we come back to how much we know about COVID-19, we know very little, frankly speaking. That's why I have been interested in natural product. Natural product, because I know vaccine, we all vaccine. I already inject 4 times. Then some of you may, I don't know how many times you inject. But even your vaccine is still infected. Nobody say after you vaccine you don't infect, right? And my idea is if I can find a natural product, red wine or coffee, or some sort of a food or some sort of drink, which can help you. I cannot guarantee you they're not infected, but can help you to prevent. So just say, assuming he drinks red wine, I don't drink red wine. And then if we were infected by the same dose of SARS-CoV-2, his chance to receive, to be positive would be less than me because he has some protection. But it doesn't say he will not be infected. It's all relative. Oh, by the way, since I mentioned that, since you're my friend anyway, you're my friend, right? How many people don't drink coffee? Don't drink coffee, right? Start to think about the drink coffee. We have data, coffee, ingredient of coffee, anti-SARS-CoV-2. And when I say we have the data, not just like the one I showed, tannic acid. We have human data now. Although human trial is so easy to do. It's different from cancer. Cancer clinical trial is very difficult to do. Yeah, you have to look for a patient who dying, then, right? But we just come out with a protocol. Then we announce, say, hey, we're going to do a clinical trial. We're going to give you coffee or no coffee, and you don't know. And then after that, we're going to draw your blood. Then you measure your concentration of the whatever coffee ingredient. And at the same time, we take a serum to test in the lab to inhibit SARS-CoV-2 replication and infection. And we did it already. I'm writing a manuscript now. I didn't put a slide in, but I'm writing a manuscript. The coffee data has a human data. So if you drink coffee, continue to drink coffee. You originally drink 1 cup, drink 2 cups. But you don't drink coffee, try to think about drink coffee.
Is it dose dependent?
Yeah, it's dose dependent, yes.
Okay.
Because we actually, when we do a human trial, we have a 1 cup and 2 cup, and 200 milligram and 400 milligram, and higher dose is working better. Yeah, dose dependent is important.
Or cappuccino, does it matter very much or not?
Yeah, it doesn't matter. It doesn't matter it's cappuccino or original coffee, and it doesn't matter it's instant coffee or grind coffee, because you know why? I only drink instant coffee because I save time very quickly. And my postdoc always uses those fancy coffee. I say, hey, come on. But I don't care about those fancy coffee. I just need to know the instant coffee, does it work? It works. It's all the same. So, and then I was joking that once we finish manuscript, we're going to have a news release. Then I believe Starbucks coffee will be a long line. Starbucks coffee is a very popular in Taiwan. Decaf is working too. Caffeine also has the ability to suppress SARS-CoV-2, but inside coffee there are some other components stronger than caffeine. Caffeine also inhibit, but decaf coffee still work. It's not work. The activity is not as strong as the regular coffee, but it's still working. Yeah, this is the question. I know if we will announce it, the news reporter is going to ask me just like why, and how many liters I had to drink. So people are going to, hey, how about decaf coffee? So we test that with decaf coffee working, regular coffee working, instant coffee okay, and or whatever. As long as it's coffee, that's okay.
Well, what's about green tea then? Green tea?
Yeah, okay. So after coffee, I have human data. Tea, we collect 40 different kinds of tea from Taiwan. And I want to be geographically, democratic country, okay? So Taiwan is not too big, it's shaped like that. So we on purpose select the tea from different area. To cover north, south, east, and west, 40 different kinds. Experiments are going right now. And some tea has activity to suppress SARS-CoV-2, some tea don't. So we are trying to figure out, we don't have complete answer yet, but we are working on that. That, as I said, I'm interested in the natural product, and the natural product is, Taiwan is an agricultural, I should not say agricultural country, but we have a lot of agricultural product. And so coffee, grape, and we talk about tea, tea, but tea I'm not complete yet because maybe at that time it was a mistake. I collected 40 different kinds. And so then the amount of work is increased. But I like to know which kind really do and which kind don't do, and then why that's the case. So we continue to do that. Yeah. So tea, I know it helps, but I don't know which kind yet. But coffee, I know. Coffee, drink, please. Anti-SARS-CoV-2.
Hopefully next time we'll know.
Oh, next time I will know it. Tea, by next year I should know. By the end of this year I should know the tea result. Question.
After coffee and tea, perhaps it's time to ask about wine, but I first would like to ask about cancer treatment. So when synthetic lethality is implemented as anti-cancer therapy, these normal cells, non-cancerous cells, still lose some important function. And in addition, usually some damaging treatment is also implemented. And actually we know that by this damaging, it is classical way to get cancer. So do we have to care about this, how to not get cancer during such anti-cancer therapy during synthetic lethality?
Okay, let me try to repeat the question. Since you're my friend, so I disclose. If I take out this one, I take out this one. I have no idea what you're talking about. And so even I wear it, I can hear what you talk, but sometimes when the very long distance, I sometimes catch, misunderstood what I mean. Yeah. So I usually, when people ask me questions, I repeat the question just in case I might. So your question is, say, target therapy, right? So target therapy is selected to target cancer cell, but not normal cell. However, whatever you target, every gene is a normal gene, right? So even target cell, even target a therapy, you target the cancer cell, but you also at the same time target normal cell. Is that your question? Yeah, okay. Very good question. Then let me start from chemotherapy first. Why people don't like chemotherapy? Because chemotherapy has no target. Chemotherapy is meaning you got a cancer, fine. I use a very toxic compound to kill cancer cell, but at the same time kill your normal cell. That's why chemotherapy has a lot of side effects, which everybody knows. Now, target therapy, in principle, ideally, target therapy is to only develop a drug to select kill cancer cell, but not normal cell. However, as you pointed out, it is practical, that's not the case. But however, it's quantitatively, that's the case. Let me using HER2 neu as an example. HER2 neu is one of the genes overexpressed in breast cancer and ovarian cancer. And when cancer cell HER2 was overexpressed, the level of HER2 in the cancer cell is 100 times higher than normal cell. So now, if I develop a target therapy, selected target the HER2 positive cancer cell, do I also at the same time kill the normal cell? Yes, because normal cell also express HER2. However, because the normal cell, the HER2 level is 1 unit, cancer cell is 100 unit. Therefore, there's a therapeutic window. Certain type of dose will select to kill the cancer cell than the normal cell. That's where the target therapy concept comes from. Target therapy does not say you will not touch normal cell. It's just saying the dose you selected, it preferentially kill those overexpressing cancer cell. But under this dose, your normal cell was okay, or it's tolerable. I think that's the case. Did I answer your question? Thank you.
Yes, actually, that was my question, but do we have any also recommendations how long it is safe to use this lethal, synthetic lethality anti-cancer therapy, or we can use it forever?
Your question is, when you treat a cancer patient, how long treated? Is that correct? Right? How long?
How long is safe?
How long what?
How long is safe to treat?
How long is safe to treat? Okay. If you are treating with the chemotherapy, you probably know better than me. Chemotherapy is very toxic. You're very sick. And I believe 50 years ago, or even 30 years ago, before target therapy available, some cancer patients died not because of the cancer, because of therapy. Because therapy can be very toxic. So for those chemotherapy, you do if they induce a side effect, your patient cannot be treated for a long time. However, if you use target therapy, and if this particular target therapy is relatively safe, if the dose is low enough, relatively safe, it can last for a long time. So it depends, from case by case, it's different. From case by case, it's different. We are extremely interested to looking for prevention. So for high-risk patient population, we some sort of a coffee or red wine or some sort of food that has an ingredient to prevent from cancer to recurrent. And since that's a natural food, so you are not worried about potential side effect. All those drugs always have side effect. So to answer your question specifically, say how long an anti-cancer drug should be treated with the patient from case to case is different. Chemotherapy certainly is not a way to do it, but a lot of target therapy, their side effect is very minimal, and those drugs probably. Now many of those kinase inhibitors will take daily, every day. Will take it every day because they don't have a severe side effect. But if they have a severe side effect, then you have to consider the pro and con. Okay? Thank you.
Since my background is not medicine, my background is bioengineering. Yes. So may I ask in Chinese? Okay. Yeah. 就是根据我们的理解，就是我们知道那个病毒它会进化，病毒它自己会变化，然后那个病菌它也会有抗药性。那像这个 target therapy， 我们是针对那个cancer cell。那经过这个 target therapy 之后，那个 target cell 会不会变化？它会不会具有抗药性
Okay, the question is following. Let's talk about COVID-19 virus. COVID-19 we are from Wuhan started, then Alpha strain, then Beta strain, Gamma strain, Delta strain, Omicron strain, right? What does strain mean? Mutation. They are very high frequency mutation, right? So his question is, now we talk about target therapy. We talk about anti-PD-1 or PARP inhibitor, this type of target therapy, and treat the cancer cell, will cancer cell also like a virus and mutated and become resistant? The answer is yes. Yes. It happened, and we are all doing that. So virtually every anti-cancer drug, if you use a single agent treatment, I guarantee 100% eventually will develop resistance. But one way to prevent it from recurrent of resistance to develop is use combination therapy. Because one drug treat with the cancer cell, the chance of cancer cell make a mutation rate and to become a mutate such a way to become resistant to this existing drug, the chance is 10 to minus 6. 10 to minus 6 is 1 million. So tumor cell is, 1 billion of cell, right? So it happened. But if I have a two drug, target the same target therapy, and their mechanism are different, then using two drugs to kill this cancer cell, to allow this cancer cell to develop resistance, the chance is 10 to minus 6 times 10 to minus 6. It's 10 to minus 12. It's still possible, yes, if you live long or 1,000 years. But the thing is that before that you already die. So the chance to develop resistance will be much lower. That's why we are all very interested into when I talk about it in the talk, a lot of stuff is combination therapy. When you use, if a cancer patient come in, you diagnose, you use combination therapy to drug directly, the chance to develop recurrent is less. I cannot say it's impossible, but its chance is much lower. But they certainly develop. Oh, hey, come on, cancer cell is very smart. Cancer cell is very smart. In Chinese, 道高一尺，魔高一丈. Yeah, the cancer cell is not smart. The cancer cell, they want to survive, just like COVID-19. COVID-19 is so smart that they know human beings going to kill them. Therefore, they mutate such a way to become Omicron. Omicron, we don't kill them. We say, okay, fine, I don't have a serious symptom, then we live together. But if COVID-19 continues like a Delta strain, we had to kill them. Right? So in order to survive, they mutate such a way. How about I become Omicron? Omicron, you don't kill anyway, so I live. Okay, that's my interpretation.
Yeah, but if to continue about COVID mutations, so now even questions still Omicron, because so lot of mutations. So one thing, and second, if we have now so huge immune press, so many vaccinated people and so on, so now very good chance for virus to keep mutating.
Yeah. So at the time Omicron just came out last year, I was joking to some of my friends. I said, hey, because this mutant doesn't cause a severe symptom, right? So this might become a nature occurring vaccine. Nature occurring vaccine because everybody got infected. In Taiwan, there are more than 30% of positive already. So it becomes vaccine. However, having said that, your point is well taken, but they continue mutating. And today, Omicron, it's okay. We don't care because they don't kill us. But is it possible Omicron continue to mutate in such a way their lethality become like a Delta strain? Hey, then that's different. Then Delta strain infection activity is not as high as Omicron. Omicron is a super infection. But it's okay because it's not doesn't kill human being. But if they are super infection, the high infection efficiency, and still damage human being, then that become very serious. Therefore, those are scientific fiction movie, we have to be careful. They might come true. There are a lot of scientific movie. At the time when we were little, we look at the scientific, but when we grow up older, they become real. That might come. Who knows? Omicron is, therefore, what I'm trying to say is, government, don't stop funding. science has to be continued because you do not know when human being is going to face another challenge and when the challenge comes, we have to be in a very short time be able to defend. Just like COVID-19 was not too bad. COVID-19 only 3 years. It used to be you develop vaccine, it cannot be so fast. But now because of COVID-19, now the vaccine development product is so quick. So, I mean, we have to improve. If a human, as a human being that we want to survive, we better be careful. Because of Omicron is so, infection rate is so high. But because they don't cause severe symptoms, so it's okay. But just in case they mutate such a way, also very lethal, then that can be very serious. So convince your government, and I cooperate to convince my government to put the money in so we can do research.
Okay, in this case, you show you can mask. What about mask mandates? If you understand that airborne virus could not be stopped by mask. But now, if especially it was being damage for kidney and so on.
So, look, we use COVID-19 because of COVID-19 we face it. But in addition to SARS-CoV-2, how many viruses, how many bacteria are hanging around that in the future might become our next challenge? How do you know? We don't know. That's why we need to continue to accumulate the knowledge. And once that happens, we can take care of that quickly. Therefore, science is important. Right? Government need to support science. So when that happens, we know how to deal with it. We know how to deal with it. Hey, are you my friend now?
Yes. Especially after tea and especially after wine.
Any more questions?
Okay, so probably the final words, science needs more support from government, from all of us, should be very important for both our...
Yeah, in a way, I'm kind of joke, but in a way true. Science, you need to continue support. If you don't continue support, when that happens again, you don't know how to deal with it. Right? I mean, think about the X-ray. Now, I know you do X-ray, you do the co-crystallization, right? Used to be co-crystallization is a very difficult job, but now it's very quick. So we need to have lots of technology available that when whatever virus or bacteria come to attack us, we know how to deal with it. We know how to deal with it. Yeah. And so next time if we see each other, please say hi, say we are here and as a friend and we have a good time. I do have a good time. I bring smile all the time, right? I have a good time. When I give a talk, I have a good time. Okay, thank you.
Thank
you. Visit Taiwan.
Okay, thank you very much for attendance. And if you have any further question, please you can contact me. And I will follow.
By the way, if there's any possibility, either you or your colleague that might want to, have some sort of collaboration, or you can send your student, your postdoc fellow, come to Taiwan. I'm open. And the reason I came here is because our two countries look like a brother now. So, right? So I have to do something. I'm really open that for, if somebody want to do a PhD or postdoc or even as a PI, you were doing some sort of research lab, and then, for example, you have a lot of medicine chemistry and enzyme structure. If we have some important enzyme, and then you're interested in that particular enzyme, maybe I can cooperate with you. Okay? So science has to work together. I wish, it's a political issue. Science has to work together to move ahead. So I have a lot of students and fellow when I was in U.S. Now went back to China. And we still talk to each other, and I help them work on the manuscript. I still help them, and we have regular meeting to talk about. But officially, Taiwan and China, it's just like Ukraine and the Russian, so sensitive. But they are my students. What do you expect me to do? Right? And the science is science. But I'm very careful. I have to protect myself. If I officially have a relationship with the China university, I have to make sure Ministry of Education in Taiwan approve. Otherwise, I might, who knows, someday you see, oh, Mget in jail. I didn't do anything wrong, but it's just because I talked to someone in China, I'm in jail, then I'll be in trouble anyway. So, but if I talk to you, I don't worry about it.
Thank you.